自我介绍，介绍你们的队伍。Hi, I'm the reporter of the Team The, and here are my team members, and my name is Yang Chenxun.
Team B 你们自我介绍。
Good afternoon, everybody. I'm the reporter today, and we are from Team 我是可爱的超威大帅哥, and she is my team member, Lin Wenling, and we thank you.
So now we're beginning the competition. So Team A, go first.
Honorable judges, ladies and gentlemen, I'm from the Team The, and I'm going to present question number 6, ring order. And here is the problem statement. An oval horizontal cylinder cylindrical-shaped rotates around its axis at constant speed, and make a ring from a cardboard disc with the inner diameter roughly twice the diameter of the shaft, and put the ring onto the shaft. And depending on the tilt of the ring, it can travel along the shaft in either direction, and we have to investigate this phenomenon. And here is my outline. I'll first show you my setup, and I'll show you my analysis methods, because we need to know the position, the precise position and angle of the ring. So the analysis methods is quite important. And I'll show you my observation video and my theory, and finally my experiment. And here is my setup. I use the iron shaft with the R 1.9 centimeter, and I use a motor to rotate the shaft. And also I make a ring from a cardboard disc, and the inner diameter is 3.85 centimeters, and it's roughly twice the diameter of the shaft. And also I make a release device to release my ring, so I can control the initial angle of the ring. And also I prepare a mirror to catch I prepare a mirror because I can use only one camera to catch the image of two directions. And also I make a device to put my cell phone on it, so I can make sure that my cell phone is vertical. And here is my analysis methods. If I have a mirror and I have a camera to catch the image, and so with the mirror I can say that I have two cameras to catch the image. And if there is a point in the three-dimensional space, I can use these two cameras to catch. And with the picture I get in one camera, I can get two information. One is theta and the other is phi. And with this four information, I can calculate the exact position of the ring. And with the 3 points of the ring, I can get the plane of the ring, so I can get the angle of the ring. And here is my analysis method. And also I analyze the friction. I use four sensors to put on the ring, on the shaft, and rotate the shaft. And I calculate the normal force on the force sensor, and I can get the force of it, and I can calculate the coefficient of friction, and I get my cardboard with the shaft the mu k is 0.1012. And here I define the angle, which because the ring is rotate in three-dimensional space, so it has three-dimensional rotation. And in the rotation in x-axis, I call it theta, and the rotation in y-axis, I call it phi, and the rotation in the z-axis, I call it psi. And these three direction of rotation is quite important because it affects the motion in different ways. So I will discuss it later. And here's the observation video. First, I rotate the shape and let the ring rotate on the shape, and then I release my ring to let go. And you can see the ring actually indeed move on the shape. And here's my theory. You can see the ring have a motion to go there, so it have the acceleration right hand side. So there must be a force. And also the only contact point of the ring and the shape is that point. So I think that force might be friction. And according to friction, we know that if the friction is right hand side, so the ring might have a relative velocity left hand side. And when my ring is not vertical to the shape, and my shape is rotating like this, so the shape might have a velocity downward, and my ring might have a rotation, might have a velocity like this, and so the ring and the shape might have a relative velocity like this. So the friction might have x component and make the ring go left hand side, and like my experiment. And here is my qualitative experiment. I use two initial angle and release lengths, and they go to a direction as I expect. And here I discuss about the rotating speed of the shape and the ring, and in my experiment, the omega of the shape is 12.95, and the omega of the ring is 11.21, and the phi I get in my analysis methods is 0.4342, and I also find that the phi doesn't change a lot in my experiment. So I calculate the omega of the shape and times the cosine phi, and I get 11.34, and which is near my omega of the ring. So I get this formula: omega shape times cosine theta is equals to the omega of my ring. And also I do experiment about the velocity and my angle phi. And in this experiment, the R of the ring is 3.85, and the omega of the ring is 11.21, and the phi is 0.4342. And also in my xt graph, you can see the ring tends to be a constant speed in the late time. So, and I fit the velocity, which is at 18.919, and I calculate the psi times r times sine phi, and I get 18.16, and that is quite equals to the velocity. So in this condition, the relative velocity is equal to 0. So there is no friction theoretically. So the ring will get to a stable state. So here's the formula I get, and I transform the omega of the ring to the omega of the shape, and I get this formula. And I use this formula to fit 5 of my data, and then the results quite fit my theory. And here is my conclusion. First, to investigate this problem, we must get the exact precision of the ring so I can get the angle. And thus with this quite precise direction to my camera. And the ring travel around the shape because there is relative velocity and so there is friction. And the angle phi is almost a constant in my experiment. And the spinning speed of the ring and the shape had a relation which is like this. And the ring will finally get to a constant velocity, which the velocity is equal to the omega of the ring times close the radius. And finally we get a formula like this. And there are more to research next, like the omega of the shape, the coefficient of friction or the weight of the ring, and the angle theta. But I will do it in future. And here is my report. Thanks.
Okay, good afternoon everybody. I'm the report, and today the objection of my presentation is problem 13, waiting time. And here's my outline. First, I'll introduce the problems and talk about the experiment and use some theory to illustrate the phenomena of the motion of hourglasses, and then talks about the parameter. Finally, we'll discuss about the analysis and conclusion. And this is my problem statement. It is commonly known that an hourglass as measured by scale while falling, and we have to investigate the phenomena. For definition part, we believe that our waiting time is for hourglass, and hourglass can be a timers, and the stable flow rate is the main point to that the hourglass to be a timer. And about the weight, as the problem talks about, it mentioned about the weight, and we define it as the normal force of the system. And for experiment, we use the glass funnel and glass bottle dropper to build up our hourglass, and under it is the high resolution force sensor. And this is our observation video. First of all, we put 20 grams of sand into the funnel, and then take out the flap on the bottom of the hourglass, and then set it free. And about the discussion parts, we know that in hourglass its container is the sand, and sand is one kind of the granular material. And we also know that although it's a single state of matter, but in some situations its flow is like solid, but sometimes it acts like liquid. And we believe that the size of sand is the main point to affect the flowing rate. And we found that the big R over small r in specific range. The big R means the radius of the orifice, and the small r is the radius of set. And in some specific range, we can get the flow rate like liquid. And if the particle is too big, it will cause a very stable formation of arc in the orifice and cause jamming to let the flow can be moved very continuously. And this is the internal we will discuss about the internal motions of the hourglass. We found because of on the wall of the glass have frictions to the sand, so this part of the velocity is smaller than the upper one, so it will cause a relative velocity. So we found that if the flow rate is small, that the shear force equal to delta V over delta Y. And when the flow rate is bigger, we found that the shear force equal delta V squared over delta Y. And this is our parameters. We use three kinds of, we use three different sizes of the sand. One is 0.10 millimeters, and the second one is 0.208 millimeters, and the third one is 0.417 millimeters. And the one is the same kind of sand, is C sand, but the 0.417 is the Y C sand. And we think the radius of our flight is 2 millimeters. And this is our experimental result. We found that when we put the sand into the hourglass, and then the weight is increasing, but this part is a bit different from regular. And this is 0.208 millimeters. It also has the same phenomenon like 0.124 millimeters. And this is for the other kinds of season, that is Y season. And we found that this part is also have some increases at first. This part is for the analysis of the parameters. We know that the flow rate equal low time A time V, and we also found that the impulsive flow force is a reason to affect the weight increases, and we get the formula, and the velocity here is means the sand leave the funnel, so we can get it. And also because the elastic collections, we found that the velocity in negative position, and we can get equals V in negative directions over G time falling plus V, and V is the velocity of falling. And during experiment, we found that 0.124 millimeters and 0.28 millimeter and 0.417 millimeters have the same flow rates like the green one. And 0.124 millimeters and 0.280 millimeters have greater impulsive force, so it is present on the red one. And about the 0.517 millimeters, it is less affected by the impulsive force. We believe that it is because of the coefficients of restitutions is different, so it will cause the result. And the reason why the flow rates, the three kinds of size of sand are the same is because the radius of the overfly is very big. It is over, it's a 2 nm, but these three kinds of sand is just 0.124 to 0.417. So we found that in this big R over small R, it have not very obvious effect. And this is our conclusion. We found the weight of hourglass change with time is relative to a flow rate and the impulsive force. And the big R over small r, we choose doesn't exist any genuine phenomena, and the velocity in negative directions equal G times T following plus V plus the coefficients of the restitutions of materials. So we get that the impulsive force is affected by the coefficients of the restitutions of materials. And our flow rates, because that sand is a kind of granular material, it has a different from flowing rate. Is because liquid isn't equal to the granular material, so we have to correct the flowing rate in the future. Thank you for attention.
Continue and take a of 2 minutes to prepare the question. Thumbs up. So now Team B, you can ask some questions on Team A. Team B, go first.
We want to know what is your initial angle of your experiment.
Which experiment?
All the experiment you didn't mention about the angle.
The initial angle I wrote down here is 0.4342, which is 5, and the theta is almost vertical. So
Okay. We would like to watch your experiment video. My question is there a board to stop the rain stop?
is there a board?
Is there something?
It's in right.
Yes.
Yeah, that is
This car.
this.
So it stopped it.
No, that is my supporter to the ship.
Okay, so there is not something to stop its motion.
So yes, I only check the motion before it bumps into the ledge.
Okay, that's all, thank you.
Sorry. Can you turn to page 14? What is that graph about? The axis, the y-axis. Yes, what is the y-axis about?
Y-axis is there is the points and 1 point percent 0.05 second.
What is NT?
Newton.
Newton.
Yeah.
So that is the force.
Yes, that's the first.
So that is your measure by your scale.
Yes.
And can you show your setup?
Okay.
So is the upper one on the scale.
Upper one, not
The-
on the scale. That is separated.
So you didn't measure the upper one.
No.
So you only measure the sand hit onto
Yes.
the.
Yes.
Okay. And can you turn to page 12? So here you say shear force is equal to delta V over delta Y, and you also say the flow rate is rho AB. So you consider sand as a liquid to calculate all this theory.
Yes. I have mentioned that we need to correct it in the future.
And so okay, I will discuss it later. And how do you measure the size of the sand?
The size of sand.
You say the
the
radius of the
size.
sand. Yes.
We use net to
So I think
separate.
your radius should be in a range, but not.
Yes, in a range.
So you okay, thanks.
Okay, now you have 10 minutes for discussion.
Okay, let's start. The first question is about what do you think of the functions of L oil in your system?
I mean,
The oil.
the
The problem
impact.
has mentioned it.
Yes, I put oil on my shape and I. Yes.
My question is, what do you think of the functions of the oil?
I mean, how does it affect?
Yes, yes.
I think when my because my experiment video, my rotations and the weight of my ring is quite small, so the oil only change the coefficient of the friction, and the coefficient is a constant also. But
Okay.
when the rotating speed up, and it might be
Assistant, it's a assistant or resistant.
is assistant.
Okay, and the next is could you please explain why the ring can rotate?
Can rotate in which direction?
Yes,
You mean spin?
yes.
Well, that all because the friction. I draw on the blackboard. So here's the shaft,
Yes.
and your ring is like when your ring put on it, and because when before your ring starts spinning, the shaft will have this direction,
Yes.
and so the relative velocity is this direction. So it is this direction. So the shape might give the ring this direction.
There's friction.
Yes, that is.
And it will move forward. It will move forward.
That move forward is when you tilt the ball. And when the ring is rotated in this direction, have this velocity.
Yes.
And the shape is in this way.
Yes.
So the connect point you have the because
And what is the force? The two force. Yes.
Because the ring only contact the shape in the
Okay, I have a question. Do you have any videos to know it can travel to either directions? Because the problem have mentioned that.
Yes, this page shows either two directions. I won't change the initial angle of the ring and it can travel in the two directions.
But I believe that it is affected by this one and get it an extra force to make it change the directions.
No,
But-
I only discussed the first. I release and before it hit onto the side, the edge.
But do you have any video to let us know it will change its directions?
When it hit onto the edge, the file of it will change. So the angle, the direction might change.
But the problem hasn't mentioned you have to put something to it. I believe that the ring will travel here and then to a position and then turn, not because of this. Yeah. And okay.
So can you tell me how do you measure the density of your sand? Because the sand is actually a solid but not a liquid.
So
Yeah, so you calculate the flow rate from the density of your
yes.
sand. So how do you measure density?
Density. We haven't measured this, but we just want to use the formula to explain the similar.
And so, and in your page 14 and those data, you all figure line as a linear equation.
But it has a little bit difference for at the first time.
Okay, so and also the first I think that equations should not be just a linear equation, and also you say there is some error in the first time. I think that is
Not arrow. We have used the theory to explain one
so. Do you
cause.
think that is your experiment error or?
That arrow is caused by the impulsive.
But how about you release your device by take out the.
At first, I can draw our device. This is our device, and then we put the 20 grams of sand into it, and then use the plastic to stop it. And at the time we want to measure, and we take this out, and it start to fall into the plane for we measure.
Okay, and so you calculate the impulse force by the coefficient of restitution.
Yes.
So did you test the coefficient of restitution?
That test is just we think is a fact.
I think the coefficient of restitution in this experiment should not because the shape of all the every sand and also.
But if you put, you can say that all the sand have the same coefficient of restitution.
And also when in your sand might hit onto the sand, so that coefficient.
But at first it will hit the plane from first, so it will cause the impulsive at the first time, and then it will have a liner's processing. And because the two 0.124 and 0.280 are the same kind of sand, but the 0.417 are the other kind, so we believe that is caused by the coefficients of the restitution.
Now we have 3 minutes to make the conclusion.
The problems of the ring Euler's has mentioned that the ring will travel into depending on the tau of the rings can travel among the shape in either directions, but the reporter's video hasn't shown us the phenomenon. We just see that the rings travel to a side, and because the side is something, it will stop its motion and then give it an extra force to move to the other direction. And about our experiment waiting time, that we get that 0.124 equals 1 equals 0.00 plus 0. And the two sides of the sand are the same kinds of sand, and we found that the 0.003, this part presents the flow rates of the sand, and this part is 0.0045 and 0.0056 is relative to the impulsive force. And we think it is not an error because the other kinds of sand is 0.17 and y equals 0.003x plus 0.003. And it has obvious difference from this kind of sand, so we believe that it's not the error.
I'm the team A, and my conclusion for ring Euler is that we did investigate that the ring can travel in two directions. When release the ring in different initial angle, it can travel to the two directions depends on the tilt. And the conclusion to the waiting time is that I think that they have quite a lot data and the data is quite good, but I think they didn't prove anything because they didn't measure the density of the sand, so they can say the flow rate is equal to the low AV, so they didn't fit their line. And also they calculate the motion of sand as a liquid, and they didn't measure the information of their sand to prove that they can calculate like that. So I think their data is not valid because they only said that the flow rate is a constant and we store so yes, I think their data didn't prove their theory well. Thanks.
Okay, I want to ask Team A. Do you have to consider the method of a ring effect on this motion?
The method,
Method of a ring.
yes, I consider it. But
how
but
to
you
effect this motion?
well, when it comes to friction and we put oil on it, and we can discuss about this and the coefficient of friction is actually related to the velocity of your device and the load of between the mass of your device and also the viscosity of your oil. So, but I didn't change the mass, I didn't change the omega, and I didn't change the liquid. So that is what I'm going to do in future. But I don't need to discuss in my this report.
Thanks. Okay. Team B, I want to make sure, how do you measure your experience error? Yes.
We use experiment to fit it, to find if this is an error or is the result of the experiment.
Okay, thank you.
I can question about in A. If you a small rate but the same mass, the horizontal velocity will increase and 5.
Wow.
A little small with the same mass. But the diameter it should be twice the diameter of the tube, but use more small, a little small.
So it will be faster.
Then you see it will be faster.
Oh, I didn't test it, and I think it will not be faster if you didn't. If the radius is not didn't change a lot.
It will make a more frequency, angular frequency, or decrease the rate.
The velocity of the ring or the
So the theta you will change.
yes, you mean when the ring moves, the theta
Yeah.
will change.
When we use a small ring, the theta will change. Yeah.
Oh
So-
yes.
So you see you will move faster, and but in the same time, the angular in 不好意思，我中英文没那么好。我的意思是说，那你如果用一个比较小的环，那你的角度也变了，然后你这个地方的比如说头灯光也变了，那你觉得它会变快吗？
它的I think when you decrease the radius, you can the contact area of the ring and the shape might be larger. So I think in this condition, and because of the your ring has angular momentum, so the more force might make the ring change other angle. But I think that is more complicated, so from now I cannot predict if it will be faster or not.
if you more than cent,
Yes.
in your equation you will
What
change, make any change in
Oh,
your
yes.
diagram.
Because we found that 0.1, these two sides of the sand is the same kind of sand. It is the different kinds of thing. The 0.417 and the green one is present it is about the flow rates, and the red part is because of the impulsive force to cause an extra score to make these parts a little bit different, not just a line to go top. And we think it is because the coefficients of the residues, because there are two different kinds of
Okay.
还有教授们还有其他问题？
没有。
要给分。先听 A。8分，9分。听 B。6分，8分。
Thank you.